You think there are 13 DNS root servers holding up the entire internet? There are actually 1,954. And that lie hiding in plain sight is just the first illusion in a journey that happens in under 100 milliseconds. We're about to trace every packet, every handshake, every cache lookup that fires between your keyboard and Google's servers. Let's break down the invisible gauntlet your browser runs every single time you visit a website. You type google.com and hit enter. Your browser has no idea what that means. It needs an IP address, a numeric identifier like 192.0.2.1. Enter the domain name system, the Internet's phone book invented in 1983 to replace a literal text file called hosts.txt that every computer had to manually download and update. Your DNS request climbs a hierarchy of caches. First the browser cache, then the operating system cache, then your router cache. If all three miss, your ISP's recursive resolver enters the game and starts querying the authoritative sources. This cascade exists because DNS lookups are expensive, and the average query takes 95.2 milliseconds globally. Here's where the famous 13 root servers come in. But here's the constraint that created them. The original DNS protocol required responses to fit in a single 512-byte UDP packet. That tiny size can only hold 13 IP addresses plus the required header data. So the architects looked at that limitation and said, fine, 13 root server names it is. But behind those 13 logical names sit 1,959 physical server instances scattered across 6 continents using a routing technique called Anycast. A single request to froot doesn't go to one server. It goes to the nearest of 354 instances. Meanwhile, broot operates just 6 instances total. The distribution is wildly uneven. The root server doesn't know where google.com lives. It only knows who handles .com domains. It points you to the .com top-level domain name server. That name server points you to Google's authoritative name server. That server finally hands you the actual IP address. This entire recursive chain typically takes between 20 and 120 milliseconds. Under 50 milliseconds is considered excellent performance. Here's what a real DNS query looks like under the hood. Your resolver asks for an A record, the IPv4 address. The response comes back with the IP, a time-to-live value that controls cache duration, and metadata about the authoritative source. But DNS was architected in a more trusting era when security took a backseat to functionality. In 2008, researcher Dan Kaminsky revealed a fundamental vulnerability, allowing attackers to poison DNS caches and redirect victims to malicious sites. The attack could distribute malware, steal credentials, and enable phishing at massive scale. The fix is called DNSSEC, DNS Security Extensions, which adds cryptographic signatures to DNS responses. But despite existing since the 2000s, global adoption remains incomplete. The protocol works, but deployment is hard. Legacy systems, configuration complexity, and performance concerns all slow rollout. The Internet's address book still has trust issues. You've got the IP address cached. Now you need to actually establish a connection to that server. TCP, the Transmission Control Protocol, starts every connection with a ritual handshake. Your browser sends a SYN packet saying, I want to talk. The server responds with SYN ACK saying, I acknowledge your request, and I also want to talk. Finally, you send ACK confirming you heard the acknowledgement. 3 packets just to establish that both sides are ready. Each packet also negotiates parameters like maximum segment size, window scaling, and whether selective acknowledgements are supported. These settings determine how efficiently data can flow once the connection is established. TCP prioritizes reliability over speed. Every byte is acknowledged, every lost packet retransmitted. This reliability costs time. If you're on the US East Coast connecting to a server in California, each round trip adds roughly 60 milliseconds. That's 60 milliseconds just to shake hands before sending a single byte of actual data, and we haven't even gotten to encryption yet. TCP is connected, but everything you send is still plain text, visible to anyone watching the network. Time to layer on transport layer security. Transport layer security replaced the older SSL protocol and handles encryption for HTTPS. The process starts after TCP connects. The client sends a client hello listing, supported cipher suites, and TLS versions. The server responds with server hello, picking a cipher suite, then sends its digital certificate proving its identity. Your browser verifies that certificate against a list of trusted certificate authorities baked into your operating system. If the signature chain checks out, both sides derive shared encryption keys. In TLS version 1.2, this entire dance required 2 full round trips on top of the TCP handshake. Here's the TLS 1.2 handshake in detail. Notice the backs and forth. Client, hello, server hello, certificate, server key exchange, server hello done, then client key exchange, then finally change cipher spec and finished on both sides. Every line is another negotiation, another potential attack surface, another round trip adding latency. Those round trips have real consequences. Every additional handshake message means waiting for packets to cross the internet and back. For mobile users on cellular networks or anyone far from the server, those milliseconds compound into seconds. And during that time, your browser shows nothing but a blank screen. Enter TLS version 1.3, standardized in August 2018 after years of development. It cuts the handshake from 2 round trips down to just 1 by combining and simplifying the negotiation steps. That architectural change saves up to 100 milliseconds per connection and reduces total handshake overhead by 56% on average. TLS 1.3 also removed older, vulnerable cipher suites entirely. No more RSA key exchange, no more CBC mode ciphers that enabled padding Oracle attacks. The spec mandates forward secrecy, meaning even if a server's private key leaks later, past encrypted sessions remain secure. Faster and more secure. That's rare. Why does shaving 100 milliseconds matter so much? Back in 2006, Google's Marissa Mayer revealed that adding a delay of just half a second caused a 20% decline in traffic. Amazon found that every 100 milliseconds of latency cost them 1% of sales. Speed isn't a luxury, it's revenue. By 2024, over 90% of major web browsers and servers support TLS 1.3. Chrome, Firefox, Safari, Edge all default to it. The remaining 10% is mostly legacy enterprise systems, embedded devices, and organizations that can't afford the downtime required to update and test encryption changes across their infrastructure. You're encrypted, connected, and authenticated. Now you can finally send the actual HTTP request asking for the web page. Plot twist, you're probably not actually talking to a Google data center in California or Iowa. You're hitting a CDN edge server maybe 3 miles from your house. Content delivery networks emerged to solve a fundamental physics problem. Light travels through fiber optic cable at about 2/3 the speed of light in vacuum, and you can't optimize physics. So instead, you move the data closer. Google operates 37 data centers across 26 countries, according to Google Cloud Platform data. A single campus can sprawl across 2 million square feet and consume enough electricity to power a small city. But those massive facilities are for compute and storage. For serving web pages and static assets, edge servers distributed globally do the heavy lifting. CDNs cache static content like images, JavaScript, CSS, and even entire HTML pages at edge locations worldwide. When you request a page, the CDN checks its cache. If the content is fresh, the edge server responds directly in milliseconds. Cache miss? The edge server fetches from a regional cache, or the origin server, then caches the response for the next user. The CDN market has exploded. In 2017, industry analysts predicted the market would reach $4.5 billion. The actual value that year was $7.3 billion, nearly $3 billion higher than forecasted. By 2025, the global CDN market hit $30.5 billion. Projections for 2034 estimate $170 billion. What's driving this explosion? Video streaming? As of the 2022 Global Internet Phenomena Report, video accounted for 53.7% of all internet bandwidth traffic, up nearly 5% from the previous year. Ultra-high definition 4K streams demand 25 to 50 megabits per second per user. Standard definition needed under 5. The bandwidth gap is 10 times. Geographic distribution is lopsided. North America holds 43.67% of CDN market share as of 2024, but Asia-Pacific is advancing at 18.6% compound annual growth rate through 2030, the fastest of any region. The next decade of internet infrastructure isn't being built in Silicon Valley. It's being built in Singapore, Mumbai, and Jakarta. Here's the market disruption nobody talks about. Netflix, YouTube, and Disney Plus each crossed 100 terabits per second average peak traffic in 2024. That's 100,000 gigabits per second. At that scale, building your own CDN infrastructure is cheaper than paying a third-party vendor. The largest players are insourcing. The CDN market is bifurcating into hyperscalers who own infrastructure and everyone else who rents it. Netflix operates its own Open Connect CDN. Google has its own edge network. Amazon CloudFront serves AWS customers, but also Amazon's retail traffic. Once you cross that 100 terabits per second threshold, the economics flip. Capital expenditure becomes cheaper than operating expenditure. Your browser sends the GET request with headers specifying the host, accepted encoding methods, and connection preferences. The server responds with HTTP 200 OK, the HTML content compressed with Brotli encoding, cache control directives, and critically, that Xcache header. That header tells you whether you hit the CDN cache or reach the origin server. Most of the time, it's a cache hit. The HTML arrives and your browser starts parsing. It discovers linked resources like CSS, JavaScript, images, and fonts. Modern browsers open multiple parallel TCP connections, typically 6 per domain, to fetch these assets concurrently. Each one goes through the same DNS, TCP, TLS, HTTP cycle unless connection, reuse, and caching kick in. Let's put the timeline together. DNS lookup averages 95 milliseconds, but can be as low as 20 with good caching. TCP handshake costs 1 round trip, call it 30 milliseconds for a nearby server. TLS 1.3 handshake adds 1 more round trip, another 30 milliseconds. HTTP request and response is a final round trip. Best case total with optimal conditions and nearby edge servers, under 100 milliseconds from key press to first byte. Worst case? DNS timeout and retry adds seconds. TCP packet loss triggers retransmission delays. TLS certificate validation fails, and the browser shows a scary warning. CDN cache miss forces a trip to the origin server halfway across the world. That 100 millisecond best case can balloon to 5 or 10 seconds. Every layer is a potential point of failure. You type a URL and hit enter. Your computer queries nearly 2,000 distributed DNS root server instances using Anycast routing to translate a domain name. It negotiates a 3-way TCP handshake, then executes a cryptographic TLS handshake that was optimized for years to save a single round trip. It pulls data from a CDN edge server physically closer to you than your nearest coffee shop, all choreographed to happen faster than you can blink. The modern internet is a monument to obsessive optimization. Engineers spent decades shaving milliseconds off handshakes because research proved that half a second can kill 20% of your traffic. Billion-dollar markets emerged just to move static files closer to users. Every layer you just traced is a careful compromise between speed, security, reliability, and cost. And none of it is guaranteed. DNS can be poisoned. TCP connections can be hijacked. TLS had exploitable vulnerabilities for years. CDNs can fail catastrophically and take down half the internet. We built a system that works so reliably that we forget how fragile the underlying protocols actually are. 100 milliseconds of magic built on decades of incremental fixes to fundamentally flawed designs. Now go type a URL and feel the weight of those invisible handshakes. Or just, watch another video. Your DNS cache is warm anyway.